Hey, 13 diplomas, and welcome back to topic 17. This is part B. So here's another question, just carrying on. We're going to do 2 more tasks and then we're going to move on to some different types of calculations. So this is task 3. It says 1 mole of ethanol and 1 mole of ethanoic acid are dissolved in an inert organic solvent to produce 1 decimeter cubed of solution and heated in the presence of a catalyst, sulfuric acid. When the equilibrium is reached, 0.6 moles of each reactant remains. So here's your equation. So this is making an ester. This is what we'll do a bit later on in the year in organic. So we're just chucking what we were given. So you were given 1 and 1 and you were told 0.6 of these existed. So if that's the case, then that means that these had to go down by 0.4. It's all a 1 to 1 to 1 to 1 ratio, which means this has to go up by 4. And therefore we have our equilibrium concentrations, and that's nice and straightforward. We can just plug into our KC, products divided by reactants, and there we go. Okay, now what I don't like about this question is you will see in the equation that these are all liquids, and that actually you wouldn't include liquids in a KC expression. So just pretend all of these for the sake of aqueous, and we're just doing it as a number practice, okay? So aqueous. All right, so this one's quite a hard task. So sulfur dioxide is oxidized in the presence of a catalyst, vanadium oxide. In this reaction, 2 moles of SO2 and 1.4 moles of O2 are mixed in a 3 decimeter cubed container, so don't forget about that, and the system is allowed to come to equilibrium. At 700 K, a conversion rate of 15% is achieved. Calculate the equilibrium constant for this reaction. Now, I know this is a 3 decimeter cubed question, but my advice is actually to leave these moles because they're kind of annoying numbers as is, and then at the end divide your final answer by 3. So here's the equation. SO2 plus O2 goes to SO3, and so to balance it, it's a 2 to 1 to 2 ratio. Okay, so a 2 to 1 to 2 ratio. So we look at the information you're given 2 here, 1 here. Now that's all we were given, okay? So we know that the change has to be -2 here because it's a 2 ratio, -1, and this has to go up by 2, but we didn't have anything else. Well, we kind of did. They actually gave you an extra part in this question, and they said it had a conversion rate of 15%. And what that means is that there's a conversion rate that SO2 will convert to SO3 by a rate of 15%. So if we times that initial value of 2 by 15%, it tells us that we get 0.3. So therefore the concentration of SO3 at equilibrium is 0.3. That's how much we had. So if that's how much we had, and we know that SO3 is that 2x factor, that means that 1x must be 0.15. And so we have to use that conversion rate to help us get to the answer. So I'm just going to say that one more time. The conversion rate tells us how much SO2 is converted to SO3, and they said it did it by efficiency of 15%. So if we times the initial concentration by 15%, we get an answer of 0.3. So that means that that's the concentration of SO3. It's 0.3. Now we know that this reaction was a 2 to 1 to 2 ratio, so that means that SO3 was the factor 2, so it's already accounted for that. They've told us that that's how much concentration that you're going to have. So therefore, because that's 0.3 is 2x, 1x must be 0.15, and we're going to use that in our answer. So let's carry on with our table then. So this is minus 2x minus x plus 2x. So we know x is 0.15, so 2x is going to be 0.3. We know that minus x is 0.15, so it's going to be 1.4 minus 1.15, and you get 0.125. And then here it's minus 2x, so 2 minus 0.3 gives you 1.7. And then to all of those values, because the container said a 3 decimeter container, you need to divide it by 3 to get these values. Then what you can do is do your KC, plug it all in, and there's your KC value, and it's quite small, which means more reactants than products. Hope that makes sense. You will have to practice these. Don't worry, you will get time. So here's the second type of calculation. So the first type of calculations that we've been doing is all solving for Kc. So this time is where you're solving for the concentration of something. Now, with this sort of question, you have to be given the Kc and you have to be given some of the equilibrium concentrations. So in this example, they've given you an equation to make methanol from carbon monoxide and hydrogen, and they've given you a Kc, and they've given you two concentrations of CO and H2, and therefore you have to solve for methanol. So it's not too hard. We write our Kc, and then we just rearrange. You're given the Kc, you're given the product, so therefore you times these two up here, and you should be able to do that easy peasy, and you get given an answer like that. Okay. Calculation 3, this is the third type of calculation. So this is calculating equilibrium concentrations now from an initial concentration. Now in this style of question, you have to be given the Kc, okay, and you have to be given initial concentrations, and then you'll solve for equilibrium concentrations. So let's see how we do it. So this one is probably the most complicated, I would say, out of all of the ones you're going to do, because you have to do the hardest sort of maths here. Or maybe not, I'm not sure. But anyway, we'll have a look as we go through. So this equation that you're given is a 1 to 1 to 1 to 1 ratio. You can see there. So you had an initial concentration of 0.3 of each of those. No products, so there's 0. But we know this is going to go down by 1 and this is going to go up by 1 because it's a 1 to 1 ratio, which means 0.303 minus x, 0.3 minus x, x, and x. So now we actually have to plug that in, and you've got an equation to do. You've got an algebraic equation to do to solve this. Most of you should be able to do it, but when you write your Kc, these two were both x, so it's x squared, and these two were both 0.03 minus x, so it's 0.3 minus x squared, and you were given the Kc. Now, whichever way you want to rearrange this equation, I just chose to expand it all out, and you can see my working here. Not anything flash, and I ended up with a quadratic equation which I plugged into my calculator and I got given this value. You can also, if you wanted to take the square root here, times this out. Once you take the square root, take the positive value, times this out and rearrange. There's multiple ways. You need to make sure you can pause the video and you can plug that into your calculator. If you can't come up with this answer, you need to let me know and we can talk through how to do it. But it's just solving an algebraic equation, kind of a skill I'd expect you to be able to do. So now what we need to do is work out the equilibrium concentrations then. So if this is x, we know that SO3 was its initial concentration minus x, so that gives you the equilibrium concentration. NO was the same, so they've got the same, and these two products were plus x, so it's just those concentrations. And so that's how we do it. So this one here is a little bit messier because you do have to do algebra. Okay, calculation 4, so this is kind of the last part of this segment. This is calculating equilibrium concentrations if the Kc is teeny tiny. And we say teeny tiny is 1 times 10 to the negative 3. So if we've got a really small Kc, because remember Kc is product divided by reactant. And I always get you to plug in these two numbers, 4 divided by 2 and 2 divided by 4. So to get a small one, you need to have a larger amount of reactants, okay? And so what we're saying with a really small value of 1 times 10 to the negative 3 is that actually most of the reaction is staying as reactant and so remains intact. And a good example of this is your weak acids, which you should remember from standard level last year. A weak acid is one that partially dissociates in water. So basically most of the weak acid remains with its proton. And so what we can do is we can make this big assumption that the initial concentration of the reactant will be the same as the concentration of the reactant at equilibrium, because hardly any of it will break apart. So it's a fairly good assumption. It's not completely correct because we know a teeny tiny bit does dissociate, but it's pretty good. So we're going to use that assumption. So here's a question. Now you'll see that this question is done at 1,000 degrees, and that's purely so we're dealing with gaseous substances the whole time. So 2H2O gas forms 2H2 gas plus O2 gas, and they've given you a Kc. Okay, and it says that the initial concentration of water is 0.1 moles per decimeter cubed. Calculate the H2 concentration. So What we can do from the equation, first of all, see this is a 2 to 2 to 1 ratio. Okay, so the concentration of H2 is 2x and the concentration of O2 is 1x, because we don't know that, and that must mean that the concentration of H2O is negative 2x. Now, the bit of information they gave us was the equilibrium concentration of water. Well, sorry, they gave us the initial concentration of water, and we know because so little of this is going to dissociate that this is going to be the same value. Okay, so this is going to be the same value because so little of it dissociates. Okay, that's what we can tell from the teeny tiny Kc value. So if you see a teeny tiny Kc value, what you should think to yourself is, aha, my reactants concentration is not going to change. That's going to be the assumption, that very little of it breaks apart. So therefore, we're just going to say this concentration is 0.1. So now we know this is 0.1, then we can carry on with our calculation. So what we can do is, I'll just go back for 1 second just to make sure that everyone saw this. So this is 2x, and this is 2x, and this is x. Okay, so H2 is 2x and O2 is x, and this is 0.1. So with that knowledge, here's our equilibrium constant, products divided by reactants. So the water we were assuming is 0.1 because hardly any of it's going to break apart, to the power of 2 here. And H2 was 2x, so 2x squared, and O2 was x, so x here. And that was the Kc, the teeny tiny Kc, which was much, much smaller than 1 times 10 to the negative 3, which is why we can use this assumption. So if you expand out these brackets, 2x squared times x equals 4x cubed. And then if you do 0.1 squared, you get this. And so therefore, if you times this by this, you'll get this. So therefore, rearranging and taking the cubed root of this, of that divided by 4, you'll end up, that should be up here, sorry. You have to rearrange and solve for x, but how they've done that is the cubed root of 7.3 times 10 to the negative 20 divided by 4, and that'll give you this answer here. So make sure you can do that. And then the final thing is that if that's x, then hydrogen was 2x, which will be 2 times that number, so 2 times x. Okay, hopefully that makes sense. Here's some questions, 19, 20, and 21 that I'm going to get you to do for homework, and we're going to stay on this for, make sure we can do it for probably another lesson. Okay team, thank you, see you soon.